Hello, I am here today to talk about a new project called Syntax Tree. My name is Kevin Newton, and you can find me online at KDD Newton, and currently I work on the widget team at Shopify. Syntax Tree was a project that came around with the last round of the Ruby Association grant. It was pitched as a project to build a new standard library Ruby formatter. It has evolved since then to provide a lot of other tools and to back various other implementations of language servers and linters and things like that. There are a couple of pieces that go into building something like this, and I'm going to talk about each of those pieces in turn. The first is to actually build a syntax tree from an input source. The next is to format the syntax tree. On top of that, I was going to build a CLI to interact with that formatting tool. After that, I built a language server that would interact with your IDE in order to build this functionality directly in. And finally, I'm going to talk to you about translating the syntax tree into other syntax trees and the implications that that has. So first step, building a syntax tree. For each node in the tree, I needed to define the shape and the types and various methods that were going to be common to each kind of node. This is the general shape of one of the nodes in the trees. You can see it has, for this instance, it has a vcall, which is basically a method call that can be either a method or a local variable. It has a value, which is the actual identifier that is housed inside of it. It's got a location, which is the location in source that the node came from. This is important and differentiates it from things like Ripper because it has location information for every node in the tree. It also has comments, and comments are any inline comments before or after or on the same line as this node. Every node in the tree has comments. Those are the named fields that are available to it, location and comments. The next two methods I want to talk about are accept and child nodes. Child nodes is a way to iterate over the entire tree, walk through the tree for every single node in the tree. It provides a common interface. Accept is necessary for the visitor pattern, which we'll talk about in a little bit. But basically, this is the double dispatch visitor where it accepts a visitor and then it calls back into a specific method on the visitor using self as an argument. Finally, every node in the tree responds to deconstruct and deconstruct keys, which allows for pattern matching. I think one more important point to point out here is that every node in the tree is immutable. All of the fields are attr readers. It's meant to be immutable. It's meant to be used in this way as like a final construction, and then if you want to mutate the tree, to use other tools to do that. So when defining each node, it's important to note how many different nodes there are. Ripper is the standard library that is another parser generator generated from the grammar file of Ruby, and it's the thing that I use to build the tree. There are 190 different unique Ripper events. Not every one of those corresponds to a node, but a lot of them do. You can see that there are a lot of different node types within the tree. Every single one of them has all of those things defined on it that we just talked about. There's a reason it's slightly less. A lot of the times Ripper has more like events. You're dispatching events, whereas syntax tree are the nodes that you build from those events, and things like keywords new and keywords add become one node in and of itself. So briefly, I'm going to talk about how we use Ripper. Ripper has kind of an interesting syntax where it is built into the parser grammar file, and inside of the grammar file, it has special comments. And those comments look like this. They have logic inside of them, and basically these get pulled out in a preprocessor to generate another grammar file that then gets written with Bison to then generate the Ripper parser. You see this dispatch one. This is where the actual event gets dispatched out to the calling code, and so this is where we access this information in our parser. So, for example, if you wanted to parse the following code, this is just an example, you could build a subclass of Ripper that would handle it like this. You have all of these on methods that handle the dispatched events. For example, onConst is going to get called when that foo is accessed. OnConstRef it's going to get passed up to the parent. So the value from the instance variable there with @const, that's going to get passed up the tree. OnIdent is then going to get called, and onVcall is going to get called with the result of that. Finally, onDef is going to get called with all of that content. And as you can see, we're building up the tree from the bottom. So looking at this parser, you know that there's a couple things that we don't quite have. We don't have any location information in it here. And by default, Ripper is only going to provide you location information on the leaves of the tree. So just the scanner events. So things like const and ident there. But onClass isn't going to have anything. But there's no more arguments to this method, so we need to take care of it ourselves. So unfortunately, the way that we end up doing this is we end up keeping a stack around of the various tokens as we find them. So we're going to scan for tokens for keywords and keep them in a stack. And it looks kind of like this. So we're going to push onto a stack whenever we get a keyword. And then in the onClass handler, we're actually going to find the most recent version of that keyword, pop it off, and put it in as our location information in order to get those kinds of tokens. Those kinds of tokens are really necessary if you want location information. And it's necessary for formatting because you can have comments in various places. You need to know exact location information for any one of these nodes. Notice that this is different from just a general AST, which is going to have, it's an abstract syntax tree. It doesn't have to be linked directly to the source. It's just representing the general idea. This is more moving towards the idea of a concrete syntax tree, which has actual location information from the source. So, right, as we said, we keep each one of the keyword nodes onto a stack and we pop them off. And so in syntax tree, what we do is we keep a stack of all of the different kinds of tokens that we might need, and we push and pop them as necessary in order to keep track of all those different things. One other example that's kind of interesting from syntax tree is we can actually handle things that Ripper doesn't. Ripper is maintained through these comments inside of the parse.y, but it's incumbent on the maintainers of the parser to go and do this, and sometimes they don't because Ripper previously hasn't had like a big consumer of it, or at least not one to my knowledge that has used it in such an extreme way. So one thing that I found when I was working through translating this syntax tree, which we'll talk about in a little bit, was that we have block local variables declared inside of a lambda. And this works in Ruby. The local 1 and local 2 can shadow outer variables and they won't mutate them inside of the body of the lambda. And Ripper doesn't handle this. Ripper doesn't give you access to these things. So we actually need to parse them ourselves. And because there is this object layer on top of syntax tree, on top of the parser, we can actually kind of abstract over that. And for newer versions of Ruby that may provide this functionality, if my pull request gets merged, then we can just use the Ripper events. But until then, we can provide this ourselves by writing like a little mini parser, which is that lambda locals function call. Finally, one of the more difficult part, I would say more than 50% of the work for this, is comments. Comments can really go kind of anywhere. You can see all of these snippets are valid Ruby. And if you're going to write a formatter, then you need to have them be respected. And this becomes very difficult. So the approach that I ended up taking was every time a scanner event is dispatched for a comment, I keep a massive list and I just throw them into the list such that at the end, when we finally have the AST, we can go and find all the places where these comments should be. And this happens by accessing that location information that I talked about earlier, descending down into the tree until it finds the preceding node, the subsequent node, and the enclosing node, and through a binary search, and eventually just finding the node that we think is the closest. It's going to favor nodes that are immediately following it because that's kind of the standard. And so you can see it just gets thrown into the tree in this way. Then when we're formatting the tree, and when we're formatting any given node, it will format the content of the node, but then it will look and see if it has comments and format those as well. So, walking the tree. I want to talk about this briefly with the visitor. This actually, I didn't have this in the initial release of syntax tree, but at Shopify, they decided to start using it for their LSP. And one of the more difficult pain points of dealing with this was not having a visitor. So this stemmed out of that work. This is the basic shape of the visitor. The visitor has a visit method, which visits a node, and it calls .accept on that node, and it passes in the visitor as its first argument. It also has a visit child nodes method, which goes and calls child nodes on the node itself, and then goes and visits in order to walk down the tree. If we go back to our example of the vcall, this has this double dispatch where first you call visit, which calls the nodes accept method, and then when you get into the nodes accept method, it goes and specializes that call to call back to visitor visit vcall. So in order to walk down, we actually only have to alias all of these visit vcall, visit args, visit assoc, and any of these things to visit child nodes. And we just have to do that for every single type. So we have done that. And that allows you to walk through the entire tree on your own. This allows for some nice things, like, for instance, if you wanted to just visit every regex in your project, you could write a visitor that does this, and then call syntax tree.parse.accept and pass in this visitor. There are also a couple of visitors that ship with syntax tree, including this one, which is the JSON visitor, which visits every single node and serializes it to JSON. And it's pretty easy once you have it built in to the visitor shape to just add this kind of functionality. So yeah. So that's building the syntax tree. Now that we have access to a syntax tree, which is just a whole bunch of Ruby objects that all point to each other in a tree-like structure, we can go and format the tree. In order to format the tree, there is an existing algorithm. There are actually multiple existing algorithms. There's one paper, Wadler et al., that backs the pretty print gem. And the pretty print gem came around quite a while ago, and it's used whenever you want to convert a hash or an array or any number of objects to a string. And the idea is that it's going to build this intermediate representation that is, instead of every node in the tree being an object, it's going to have every node in the tree be like a doc node, which is a node that represents how things should be formatted. A text is just actual content. The breakable is where new lines could be inserted, and a group is a set of text and breakables that says that should be broken up together. The overall algorithm is to break the outermost groups to fit to the print width. And I'm going to show you exactly what that means. For example, let's say we have this massive array, and let's say we have a print width that's on the end of our line. Then this is fine, and we can leave everything in place. However, if our print width is in the middle of the file, then we need to break, quote unquote, the outermost group. I like using an array for this example because I think it's more easily visible that we're going to break on every top level element. And you can see that's what that looks like. Now notice that the third element in the list of bars, is not broken up because it actually still fits within the print width. So that outermost group was broken, but the inner one wasn't, because as we hit an inner group, it's going to check if it fits on the same line. And if it does, then it's not going to break it up. So if we move the print width back a little bit further, we'll see, okay, we actually do need to break that up even further, and it'll do so. So this array is actually represented by a whole bunch of nodes in the tree that are doc nodes. And this is generally what this looks like. So you can see we have all these text elements represent the actual text that shouldn't be broken up. The breakables represent new lines that should be inserted. We have a couple extra nodes like indent, which indent things whenever they're on a new line, and break group, which forces a break into all of the new lines in that group. This is the innermost group that includes the bars, and you can see these are the breakables. These are the places where new lines will get inserted if that group gets broken. That being said, these are the breakables on the top level, and those are the ones that will get broken first, because we always break outermost groups first. So when I built this formatter, I added a whole bunch of functionality to the pretty print gem, and it wasn't the best use of open source culture, I suppose, and I ended up making too many additions to pretty print, unfortunately. It was very hard to see the difference because I had added so many different features, and it was hard to use. So instead of Pretty Print, I actually just ended up publishing a new gem called Prettier Print. Prettier Print is actually a drop-in replacement for Pretty Print. You can use it in the exact same way. It just has all of that additional functionality, and hopefully one day I'll upstream it again. So in regards to the actual syntax tree, now that you understand the algorithm, there are a couple of interesting things that we can do. For instance, let's say we have an if statement in Ruby and the print width is right there at the end. We can't do anything. However, if the print width is at the end, we can turn this into the modifier syntax. I say that there are a lot of caveats there. If there's any assignments in the predicate, we can't do that. If this is inside of another if statement, we can't do that. There's a lot of different reasons why you wouldn't, but that's just an example. Similarly, with an if-else, if there is enough space, we can turn that into a ternary. We don't do it in a lot of cases, but on some we do. Similarly, with a here docs are the bane of existence for a lot of formatting. But we can do some interesting things here where we actually inline the here doc declaration and move it into the function call for formatting. So once there's enough space, we move that declaration in. Similarly, if we have this return 123 map, we can move it in. Now here, when you move the map element, the map array needs to move down, but the return doesn't actually have any parentheses on it. So we actually have to add those parentheses in. We also want to maintain the comment on the overall return element. So in order to do that, we're going to move everything over to the left. And this is all happening based on this printing algorithm, based on describing the groups, describing the text, describing how things should move and break. So this is an example. This is an if node inside. This is a predicate, and it's got two different kinds of blocks for describing how things break. So this functionality wasn't originally in prettyprint because prettyprint formats as it goes and builds up a buffer and only formats as soon as you hit a new line. In order to handle the prettyprint things, in order to handle the enhancements, I needed to build up the entire tree first and then walk down the tree. So for this, it describes if break, it's going to format it with break, and if it's flat, it's going to format it with that modifier syntax. So that is formatting. Briefly, I'm going to touch on the CLI that I created in order to interact with this. There's a whole bunch of different commands that get output when you run syntax tree help. It'll show all of these things. You can output the version. You can get access to the AST to actually print out that nice AST that you see. This can actually be really useful for debugging purposes, even just to see how Ruby is interpreting things. You can think about like operator precedence and things like that. There are a couple of visitors that are built in, that JSON visitor that I mentioned earlier, and also a match visitor, which is actually going to print out a pattern matching expression for any given Ruby input, which is very useful for finding specific patterns. Finally, there are all these commands that accept files, and they can format files. They can check that something can be formatted idempotently. You can use it in CI by running stree check, which will exit with an error if any of the files weren't formatted as you expected, things like that. Finally, I'm going to briefly talk about plugins. There are a couple of built-in plugins that Syntax Tree ships with. I don't like adding options for configuration, but because people have already kind of solidified into camps, I have added the ability to select for single quotes if you want them, or trailing commas if you want them. I also have the ability to build your own plugins, which is documented in the README. There's also a couple of language plugins, a couple of languages that I've additionally built functionality for Syntax Tree. So for all of the goodness that you've seen so far in this presentation, I've also built that same thing for the RBS type language, the HAML template language, the JSON notation language, the XML markup language, and the CSS style sheet language. More on the way. So that's the general CLI. The one command I did skip here was the LSP. So I'll talk about that next. Creating language server. Language servers came about when Microsoft decided to build a standardized protocol for interacting with its VS Code IDE. And they become incredibly popular. And the idea is to generally run a JSON RPC server behind the editor in the background as a separate process. And to respond to certain actions. So for instance, these three actions, text document, did change, did open, and did close, those all represent actions that the user is taking around specific text documents. The one that I respond to with Syntax Tree is text document formatting, which gives you a URI of a file, and you are supposed to respond with the content of the changes. of how the file should be formatted. The other one that I respond to is text document inlay hint, which is useful for showing what I do is I show operator precedence by inserting parentheses when there are none, and for instance, inserting standard error when you just rescue bear to tell you that that's what you're rescuing. This is an example GIF of how the formatting works and how fast it is. You can type however you want and then just hit save, and things just seem to snap into place. So formatting on save is definitely a possibility. So this language server has some of the bare functionality in it, and I'm adding more functionality to it all the time. However, I will say that Shopify has been investing an entire team in another project called RubyLSP. It provides way more functionality than mine does. And I want to talk about it very briefly here. It includes document highlighting, document symbols, so you can jump to, for instance, a method definition, folding ranges to fold a method or a class or a module, formatting support, as I mentioned, with syntax tree, but also with RubyKaigi, and the ability to specify selection ranges and semantic highlighting, for instance, being able to reflect on if something is a local variable or a method call. So, this is just the beginnings of making Ruby developer experience better. I'm really happy that Syntax Tree is backing this project, and I hope that I can use it in many more projects to provide the same kind of functionality. The last piece of this that I want to talk about is translating the syntax tree. Historically, Ruby's syntax tree using standard library has been difficult to access. Ripper is not incredibly well documented. There's a lot of functionality in it that changes between different even patch versions, and it's been difficult to work with. So people have typically reached for either the Seattle RB Ruby parser gem or the White Quark parser gem, or the RubyKaigi AST gem, which is just a derivation of the White Quark parser gem. These gems provide access to a parser, but it's not the standard library parser. The Ruby parser gem is provided with its own grammar, and it uses RAC, the RACC. Same with the White Quark parser. The White Quark parser also uses Raggle to generate its lexer. And it's got, they provide syntax tree availability, but this isn't standard library. And I say that as if it's a bad thing. It's not necessarily a bad thing. It's just we are relying on these people's goodwill to maintain these projects, which is a very tough thing to do. Maintaining a generated parser in line with upstream is very, very tough because there's not a lot that you can do other than just watch the commit log and hope you can maintain compatibility. So over the years, various static analysis tools have been built on top of these things, like Reek, RubyKaigi, Fasterer, any number of things that SolarGraph. All of these things use these tools to build additional tooling, and RubyKaigi isn't going away anytime soon, and we wouldn't want it to, but it uses the parser gem, so it's always necessarily going to be just a little bit behind the standard library parser. So one of the things that I am very interested in doing, and one of the projects that I'm working on, is trying to change these static analysis tools to instead use the syntax tree parser by using syntax tree and translating that syntax tree into their representation of the syntax tree as well. That work is being done in the Ruby syntax tree translator project. You can check it out on GitHub. So far, what it does is actually it can translate the existing syntax tree representation of the syntax tree, the Ruby syntax tree, and convert it into the White Quark parser or the Ruby parser syntax trees. I'm still working on the location information and comments lining up appropriately, but I already have a branch running where it can run RubyKaigi with syntax tree being the backing parser. I have plans in the future to write a new Ruby parser, which I will likely talk about at a future RubyKaigi. But hopefully this standardized syntax tree node shape will allow us to just swap these backends out and still maintain all of the great functionality of RubyKaigi or any of the other static analysis tools without sacrificing anything on speed or compatibility. So thank you very much. This has been a talk about Syntax Tree, which is a new project to provide fast parsing and formatting using only the Ruby standard library. I also want to mention that there is another talk There's another keynote here at RubyKaigi talking about Wasm, and I've done a lot of work with syntax tree to get it so that it will run in the browser. You can check out more of that project on github.com/rubysyntaxtree. You can check out all of the various projects associated with this. Thank you very, very much for having me. I appreciate it. Let me know if you have any questions or comments. I'm always available on Twitter there at KDD Newton. Thank you very much.